तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will look at the system of solutions for a system of nonlinear equations in a little more detail. That means we will be looking at equations of this form, that is fi of x1. So these are unknowns. So we look at a system of equations of this form, that is f1, f2, x1, x2, etc. up to fn So we look at this in a little more detail, how to solve a system of equations, nonlinear equations of this form using Newton-Raphson technique, which we have already used for single equation, single variable case. Okay, so we will just look at how to do that in the case of a system of equations. So the basic idea is the following, that you have the equations of this form for n such equations for n unknowns, and then we would Taylor expand these functions around a set of guess values, and then we have that guess values, so xn guess values, and we would Taylor expand this function around that guess value. And then we have the Taylor expansion now given by this, that is fi at x1 plus h1, fi at x2 plus h2, etc., all the way to xn plus hn. Right. So h1, h2, h3 to hn are the increments or in the variables x1, x2, x3, xn, and that's now given by f, the function evaluated at the guess value, plus hj into del fi by del xj equal to 0. So that's a sum here, sum over sum over j. So h1 del fi by del x1 plus h2 del fi by del x2, etc. So there will be n such equations, right? For each of the fi's, you will have such equation. There's an fi here too. Okay, there are n such equations. So in short, so we have the equation of this form, that fi of x1, x2, xn equal to 0 for I going from 1 to n, and then we have the guess values xi's for again I going from 1 to n, and then we Taylor expand this function, that is fi at x1 plus h1, x2 plus h2 to xn plus hn. We write that as fi at x1, x2, xn plus h1 into del f1 by del fi by del x1 plus h2 into del f2 by del fi by del x2. So all the way up to hn into del fi by del xn. Right? This is for all I going from 1 to n. So that's what we have. So this is the, so now we have for all the I going from 1 to n, and this is the expansion we want to solve. So we will obviously put the left hand side equal to 0, right? This term is equal to 0 is what we are going to put, and we are going to solve for this. That's what we did for the one variable case. In the one variable case, we have only one equation and only one term here. So now we have a series of such equations. So, but then we have series of such equations, we can solve them by the matrix methods which we know. So, a series of equations can now be written as H1 del F1 by del X1 plus H2 del F1 by del X2 to plus Hn del F1 by del Xn equal to minus F1 of X1, X2 up to Xn, and the next would be H1 del F2 by del X1 plus H2 plus Hn del F2 by del Xn equal to now minus F2 of X1, X2, Xn. Right. So, we have the equations n equations as like the last one ending with minus Fn of X1, Xn. So, that's a set of equations which we have to solve. Right. So, we have this set of equations to solve. Okay. So, and we know, and this all these coefficients are evaluated at X1, X2, X3, Xn, that is our guess value. Right. So, then we have these derivatives evaluated at that, and then we only have to solve for the H1, H2, Hn, etc., and then we know the right hand side of this equation, because that's again the function evaluated at X1, X2, Xn. Okay, so we will see a specific example where we use this. Okay, maybe a function of two variables. So, it will be two equations, and then we will solve that equations and get the answers. That's maybe X1 and X2. Okay, so that implementation we will see in a program here. So, the functions which we will be solving are of this form. So, we have two functions. One is let me call that as F1. So, F1 is minus x squared plus x squared plus xy. So, x squared plus xy minus 10. Okay, that's one function. And the other function F2 which you will solve is x1 minus y plus 3xy squared, 3xy squared minus 57. So, there are two functions of this form. So, F1 equal to x squared by plus xy minus 10, and the other one which we are going to look at is minus function evaluate x plus 3xy squared minus 57. Okay, so this is that's the function values. Okay, so that's the function which you are going to solve. So, the derivatives would be we are interested in is, so this derivatives, that is del f1 by del x1 and del f1 by del x2. So, x1 here is x and y1 x2 is y, which is written as x plus y. Okay, so, we have find out del fy by del x. Okay, so that is f1 by del x. Okay, that's basically 2x plus x, and then we want to find del f1 by del y, which is this x. Right. Then you have del f2 by del x, which is 3y squared, and then we have del f2 by del y, which is 1 plus 6x. So, given these four quantities, that is the derivatives and this function value, okay, the derivatives and this function value. So, we can go ahead and solve this equations by the Newton-Raphson technique. Okay. So, that is what this program is going to look at. Okay. So, this program uses the elimination technique, Gauss elimination with pivoting to solve these equations. Okay, that is what we see here. So, I have the main program in which now I have to the solutions that we are to be given as an array. Okay, and my guess values also has to be given as an array. Okay, so x1, x2. So the mapping is x1 is now x and x2 is y on this thing which I have written here. Okay, since we are more familiar with x and y using instead of x1 and x2. Okay. So that's the mapping. So my array elements now, my solution will contain now an array of x1 and x2. So is my guess values x1 and x2. So this program requires in the main program. So it calls it's going to call a function called nonlinear equation solution. So where we will pass the number of equations which we have, or the number of unknowns, that is the order of this this array, one dimensional array x. So that's in this case it's 2, that is 0 and 1, that's 2. So n equal to 2 is what we are going to pass, and then we will pass a pointer to the function func here it's called, okay, which is which returns this function, something which we provide, which returns the function value and its derivatives, right, derivatives at all, whatever value we ask for in the x variable. So then, so this main program basically just reads off the guess values from the screen, right, and then calls this function to which it passes those guess values. It also passes a pointer to that function, and the order, the number of equations or the dimension of the array x, that is that's also been passed, and it gets the solutions back in x and it just prints it out as x0 and x1. So the solutions comes back. So we give x as a guess value, the solution comes back as x here. And since I repeat this again, that since we are passing this function here, so it has been declared outside the main. Okay, and you can see the arguments this function takes in our two one-dimensional arrays and a two-dimensional array. So the two-dimensional array is the first derivative of all the functions with respect to all the variables. So that's the two-dimensional array, and this is the solution or the x values, x1, x2, that x array, and this is where the function values are returned. That's a program. Okay, that's a main program. Okay. So then we just call that function. Okay, so that's a function, nonlinear equation, this function, and the function now, okay, of course takes in this x as an array, so that's taken here, and this is our function pointer, so that's now called function, which is as I said, 3 arguments, 2 one-dimensional arrays and a two-dimensional array, and m is an integer, which is the order. So I use that m to dimension my matrices here inside this program. Okay, so this program is quite general, because you can solve with this, easily extend this to an m dimensional object. I'm solving this, whatever we are solving here is a specific example of m equal to 2, but this program is general, and you can pass any number m here and should be able to do it. Okay, so now this is the array elements, some working arrays which you have declared here. So this is a two-dimensional array and a one-dimensional, three one-dimensional arrays. Okay, this is something which we required to solve the Gauss elimination, solve the linear equation using Gauss elimination. Okay, so we start with some error defined as 1. Okay, just set it equal to 1. Okay, and now remember m is the order of our matrix here, and then we have we just print out all the matrices just to show how the matrices are evolving. Okay, so we call the function here and pass the x value. Okay, now here one more point. So we pass the function here. We call the function here and we pass the guess values in the first round. In the first round, before the iteration starts, we call for the function, and that function that's guess values, and this is where the function values and this is where the derivatives will be returned. And this d actually returns the negative of the function values. Okay, so my d in that program is written as d of I is is written as minus fi, okay, because that is the right hand side of this metric equation, right. So, this is basically the right hand side of the equation is minus the function value, and this is the Gauss elimination, the right hand side of the equation. So, that is this will get the minus of that, and d will get the second derivatives. Okay, so, that is simply the program, and then we will start our iteration loop here, okay, starting with here, and then we will eliminate, use the Gauss elimination process to get the solutions. So, Gauss elimination process, we know, we have done that in earlier classes. Okay, this is with pivoting. Okay, so that's this part of the program. So, once we come here, we have the solutions, right, and then we call the solution. So, basically S is a solution of this equation. Okay, so we write now the matrix equation of this form. So, that is del f1 by del x and del f1 by del y, del f1 by del f2 by del x and del f2 by okay, so that is our matrix equation. So, that into we will write h, when we write in this will be hx and hy, instead of h1 and h2 we call it hx and hy. Okay, so, that is equal to minus f1 minus f2. Right. So, that is the equation which we are going to solve. Right. So, once we get the solution of this equation would be hx and hy, okay, which I called as S here. Okay. So, that is what S is. Right. So, this whole program here is just a Gauss elimination with pivoting. Okay. So, that is what it is doing. Okay. So, from here onwards it is just Gauss elimination with pivoting. Okay. And so, once we come here we have the solution, SIs we have the solution. Okay. So, now once we have the solution, we have to update our x values. Okay. So, now that is done here. So, since now xi's go to xi plus hi, right. So, h is now it is just S here. Okay. So, now we have the new new values, okay, and then we will evaluate the function with the means we will call the function and its derivatives here again with the new x values, and I have declared the error here as d of 1 plus d of 0. That should be 0. The function, I am just using the function value itself here. We need not use this as the error, as we know we should actually use x of I earlier, the x of I minus the x of I new divided by x of I new as the new error value. So, I am just using simply for convenience here as a function value, but this function value as the error, okay, because we are looking for the function, the points at which the function goes to 0. So, I can use the function value as the error, but as we have seen earlier, this will have problem when the function goes to 0 very slowly. That is, the derivatives near the 0 is very small. This is not very accurate, but this is just an easy way of doing it. But you could also define this as x old minus x new divided by x new summed over all x's in this particular case. Okay, then I just print out the values here and the error which we get in this printf function. Okay, that's a program. Okay, now this is just for the pivoting, and here is a function. So, the function value evaluated here. So, this is our func function. So, it gets the x values and it returns the function values, the negative of the function value and its derivatives in a 2-dimensional array. So, this program has to be supplied depending upon what function, what set of equations which you want to solve. So, that it should be appropriately dimensioned. Okay. So, if it's here is only 2 variables, so I just put everything as 2-dimensional arrays. If there are n variables, here you put them as n by n arrays. Okay, so now we have the function value here, which is minus of x square plus xy minus 10, and the other for the f2 is x plus 3xy squared, the power function xy square minus 57. So, then the derivatives, I have written down the derivatives here, which are written on the board. So, that is 2x plus x, 2x plus y is the first derivative of the function y of 0 with x of 0, and the derivative of the function y of 0 with x of 1, and the derivative of the function y of 1 with respect to x 0 and the derivative of the function y 1 with respect to x 1. So, that is what the derivatives are. Okay, so, now we run this program and let us see what we get. Okay, so we run this and so now it is waiting for two guess values. So, we give some two guess values as 1 and 2, okay, and the program converges pretty fast and then goes into the solution as 2 and 3. So, that is the solution of the equation and you can see that the function values are gone to 0 at this point. Okay, so, I am printing out the function values here, remember. So, let us look at what all we are printing out. So, we are printing out the x 0 and x 1 values. Okay, so that and the function values. Okay, now this is actually I put in a minus sign here so that we are actually printing out the function values and this is the error. So, wherever the function goes to 0, the error also will go to 0 because it is just the sum of these two. Okay. So, the function values go to 0 at this point. Okay. So, now after this, now we will go into the next topic of this course. So far we have looked at in this particular section, we have looked at the solutions of a system of nonlinear equations and we have used them. We first started with a system of one variable equations, that is we looked at equations of this form, that is. So, we looked at equations of the form f of x equal to 0, one variable equations, okay, and then we found many methods. One method which we looked at was bracketing methods, that is, so we said mean or midpoint method we call it, okay, we call midpoint method. Midpoint method is something which we looked at to find the solution of this. So, this method had that we had need two guess values on either side of the 0, okay, and then we looked at after this we looked at false position methods, false position method that also required that we have guess values on either side of 0, that is we had guess values x1 and x0 and x1 we call it, and such that f of x0 is greater than 0 and f of x1 is less than 0. So, for both these methods we needed that, okay, so that is methods which needed two guess values on either side of the 0, and then we looked at methods which does not need that. For example, we looked at fixed point iteration, fixed point, okay, that this iteration scheme we wrote the function f of x as g of x minus x equal to 0, okay, and then we use the iteration scheme as xi plus 1 is equal to g of xi. So, that is fixed point iteration, and then we looked at what is the most popular method, that is Newton-Raphson. Okay, so we Newton-Raphson scheme in which we needed a derivative, right. So, in this particular case we needed the derivative of the function and we wrote the iteration scheme as xi plus 1 is equal to xi minus f of xi divided by f prime of xi, and then we replace this derivatives by its difference scheme using a difference scheme, and that is we call the secant method. Okay, in the secant method we simply replace the derivative by f of xi. So, f prime of xi we replace this by saying f of xi minus f of xi minus 1 divided by xi minus xi minus 1. So, then again this required again two guess values for the secant method, but we do not need them to be on either side of the 0. So, these are the methods which we looked at in the to use to solve equations of this form, and then we generalize that into a system of equations of this form, okay, and using the Newton-Raphson method. Okay. So this can be this particular method we also generalize into a system of equations. So that's a summary of the solutions to the nonlinear equations which we have looked at. Okay. So the next topic which we'll be looking at is the numerical differentiation. Okay. So as we saw in this particular method itself, in some cases we need to find derivative of functions. So in the case where a function is what we want to find is a set of data points. Okay. So we want to find we don't have a functional form. Okay. We only have a set of data points, and then we still want to find, for example, where the where it actually crosses 0, etc. Where what is the x value at which it crosses 0, and then we need approximate schemes for finding derivatives. That's one of the reasons why we went to this method in this case of systems of nonlinear equation, in the case of solution to a nonlinear equation. So there are many cases like this in engineering and science, and where we would need to find derivatives of a function, a derivative of a function, or derivative in the case of a line which passes through a set of points. So approximate schemes to find the derivatives. So the function value itself could be returned by another program. Okay, in that case we don't know what the derivative of the function is, but then we should be able to find that using some kind of approximate numerical scheme. So that's what we would discuss now. And after we discuss the differentiation methods, we will go into the integration schemes. Okay, so to summarize, when we need to actually calculate the derivatives, if you just have a given set of data points, and that's where this will be most useful. These methods which you are going to look at will be most useful when in this particular kind of cases where we have only a set of data points given and we want to find the derivative. Many of the optimization schemes which we would be interested in looking at would need derivatives of the function evaluated, and then we would need to find that some method to evaluate that. And sometimes even for solving differential equations we need to write down discrete formula for derivatives. We may want to convert, for example, if you have a partial differential equation, we will look at that cases later. In the partial differential equation case, we will again have to convert them into a set of discrete equation, and then again we need to write down the derivatives in terms of some set of discrete using a discrete formula. So there are many cases where this is actually important. So here we will look at some methods of calculating these things. Okay. So first method we will look at is that using interpolation, okay, because we already have learned how to interpolate a curve between for a given set of data points. So we will look at that now. So let's say we have a set of points. So we have some function f of x here, versus x, and we had a set of data points. So we had a set of data points, and you were asked to find the derivative of this function at any point here. Okay. I am interested in the derivative at this point. So that is at this x value. Let me call that as some xi. I want to find the derivative of this line which passes through this point, okay, at this xi. So what I have is only a set of data points, and I am interested in finding the derivative. So the question is how. So one method is that we know how to get a curve going through this point by the interpolation scheme, right? So we know how to get a curve using polynomial interpolation. We can actually get an equation for a curve which passes through all these points. So once we have the equation for that kind of a polynomial, okay, that is, let me call that some nth order polynomial Pn of x, right, which passes through all these points. Right. That is, this function polynomial takes Pn of xi as f of xi. So this polynomial passes through all these points, and then I can simply find the derivative of this polynomial. Right. So my f prime, my derivative of this line at any point in between would be just the derivative of this polynomial evaluated at that point. So that's one advantage of getting a polynomial like that. Okay. So, and we know how to write down this polynomial. For example, using the Newton's form, we know this can be written as f of x0 plus, remember there is a function called x0, x1, x minus x0 plus f as x minus x0 into up to x minus xn minus 1. So, this is something which we have seen before. Okay, so this we have a set of data points, and I can write down a polynomial, okay, which goes through all these points in this fashion. So, in the Newton's form. So, these are the coefficients which we can evaluate. Okay, the all terms in square brackets, okay, are the coefficients of this polynomial, okay, and that is related to this thing given as f square bracket x0 and f square bracket x0 x1 are coefficients which are related to the function values at x0 and x1, and we can evaluate this using a difference table. We have seen this earlier. So, we'll just write down that expression again just to remind you of what we had learned in the polynomial interpolation. Okay, so, for example, f of x0 is the same as f of x0, and f at x0 x1, that is the second, the coefficient of the first order term here is f of x1 minus f of x0 divided by x1 minus x0, and the coefficient of this third order this term was that is f at x0, x1, x2, if you remember, is f of x0, sorry, x1, x2 minus f x0, x1 divided by x2 minus x1, etc. So, it's a, so we constructed a kind of difference table, and then as a kind of recursion thing, we had a kind of recursion relation from which using which we could compute this third order terms from the second order terms and the fourth order terms from the third order terms, etc. Okay, so, here f x0 x1 is just this, but f x1 x2 will be similarly f x2 minus f x1 divided by x2 minus x1. So, we knew how to construct this polynomial. In short, we really know how to construct this polynomial, and once we know this polynomial, and then I can find the derivative of this polynomial, and then I can evaluate that polynomial at any point. Okay. So, the derivative of this polynomial then simply would be Pn of x at any point x. The derivative of this polynomial, as we can see, is another polynomial with x0 x1 plus so up to we will have f of x0 xn, and then we will have here a sum of all the terms. So now notice that the second term, now the derivative will have two terms here, right. So that's one is x minus x1 and other is just x minus x0. So you have two terms here, x0, x minus x0 and x minus x1. Okay, and then similarly the last term will now have a sum of I going from 0 to n minus 1 and j going from 1 to n minus 1, 0 to n minus 1, and then we will have x minus, sorry, this is pi, x minus xj divided by x minus xi. Okay, that is the term which we will have. So, I will summarize this again here. So, if you look at this, so we have the polynomial which goes through all these points is given by this, right. So, we have the nth order polynomial given as f of x 0, because the first coefficient is just the function value evaluated at x 0, and then these square bracket terms, as I just now told you, are related to these function values as f of x 0 minus f of x 1 divided by x 0 minus x 1, etc. And then the last term would be just the product of all the terms up to n minus 1. So, that is the nth order polynomial which we have here. Okay, and then we can find the derivative of this polynomial. The derivative of polynomial is now another polynomial which starts with this coefficient f of x 0 x 1, okay. And then it goes all the way to the last term, which is now going x minus xj product divided by x minus 1 by x minus xi. Okay. So, because second term will now have two terms, similarly the last term will now have n minus n such terms. Okay. So, the second term here is n two terms, the second order term of the polynomial is now the first order term in the derivative, which will have now two terms here, and similarly the n minus 1, the last term will have n minus 1 such terms, okay, which each of them will be a product of n minus 1, each of them will be a product of the order of n minus 1. Okay. So, that is the polynomial which we have. Okay. So, now we can evaluate this polynomial at this point, and there is some error, of course, because it is a finite series we are using. So, there is some error term here similarly. So, there is an error term here. So, there is a polynomial error and then the term, and then there is an error here. But we know what this error is, we can kind of estimate what this error is, because we have seen earlier that in the case of polynomials the error here, okay, is like the next term in the polynomial. We have seen that. Okay. So, if you look back, you will, or if you might remember, if you know, that we have written this down earlier, that in the case of polynomial interpolation, that the error in the polynomial of the nth order polynomial is like the n plus 1th order term in the polynomial. So, it is like the next term here. This error is of the order of the next term in this expansion. Okay. So, then this error here should be simply the derivative of that term. Okay. So, that way we can actually estimate the error. Okay. So, I am writing down that here. Okay. So, the n plus 1th order term, okay, is then a product of all quantities x minus xi up where I going from 0 to n, okay. And now there is a prefactor there, and the prefactor we know is the n plus 1th order derivative divided by n plus 1 factorial. That is what we have seen earlier. So, we have seen that the error in a polynomial is of the order of the next term in the polynomial. That is, if you have n or nth order polynomial, it is like the n plus 1th order term in the polynomial. So, the n plus 1th order term is simply this, that is x minus xi multiplied for I going from 0 to n, the product of x minus xi for I going from 0 to n. And the prefactor we know is the n plus 1th order derivative of the function, of the true function, divided by n plus 1 factorial, evaluated at some point between x 0 and x n. Okay, that is the error in the polynomial. So, we can just take the derivative of this, that is del p error by del x. So, that should be the error in the derivative. Okay. So, the idea here is that if you have a set of points given, we want to find the derivative at anywhere in between these points. Okay. Not only on the points where it is tabulated, but even in between this, then we would think that, okay, I can actually write an interpolation. I can write a polynomial which interpolates all these points, and then I can use that polynomial to find the derivative. So, we would think that, okay, to find the derivative at this point, why should I take all these points? Okay, I could just simply take 1 or 2 points here, maybe 3 points, or maybe just 2 points, and just draw a line and then find the derivative there. So, there is obviously an error in that, okay, and that error is of the order of the polynomial which you use. Okay. So, that is the polynomial. If you use the polynomial nth order to interpolate this set of data points, we have an error in the polynomial which is like the n plus 1th order term, okay, and hence the error in the derivative will be of something of the order n, okay, or nth order will be the derivative, the error in the derivative. A quantitative value is difficult because of the following reason, that is, the error we can write like this, but we don't know this function actually, right, because we don't know this real function which goes through these points. We only know an approximate function which is our polynomial. Okay, so we were not able to evaluate this n plus 1th order derivative obviously, and so we don't, since we don't know the functional form of this, the derivative of this with respect to x, which should actually have two terms, that is, one is the derivative of this part multiplied by this, and another one is the derivative of this part multiplied by that, right, because this is actually a function of x. Eta is some value of x between x0 and x1. Okay, so we need to know what that is. We need to evaluate the derivative of this at that particular point, derivative of the function at that particular point, but we don't know that function. Right. So we are not able to get a complete quantitative value of the error, but we can get a good estimate of the error. Okay, so once since we don't know this functional form of this f eta, we can't get a quantitative error, but we can get a good qualitative idea about the error in the derivative. So, and we also see that if you evaluate the derivative at the tabulated points, that is xi as the tabulated points, right, and then this quantity, there is only one term in the error, right, because the other term goes to 0, then we have only one term in the error, and that is just the derivative of this part with respect to x. So for any value which is tabulated, we can actually use this, the derivative of this with respect to x as the error. Again, since we don't know the functional form here, we still again only get a qualitative error, but in untabulated points we can't even get that because we simply have no idea what this quantity would be. With that caveat, we will look at a particular example of using this idea of this polynomial interpolation to get the derivatives and get some feeling, which gives us some feeling for the error. Okay, so to summarize, the error of for a tabulated point, at the tabulated point, the error in this method of calculating numerical derivative by interpolation would be of this order, that is n plus 1 derivative evaluated at some point eta between x0 and xn divided by n plus 1 factorial into a product xi minus xj. So this is now evaluated at xi, a product of xi minus xj for j going from 1 to n except at j equal to I. So that is the error it will be. So this is useful because this way of calculating the polynomial, for calculating the derivative using a polynomial is useful because it's easy to program. Once we have the difference table for the polynomial, then we can read off the derivatives also very easily from that. Okay, so we will see that for a particular example of the function f of x equal to x squared minus 2x plus 2. Right, so we will see this example. Okay, so now remember what difference table is. So the difference table I am showing here in this one is the same as what is given here. Right. So for this we can continue all the way to f of xn as simply the function value at xn. So that is the first order, first column in the table. Okay, that is so I have some index I is going from 0, 1 to 4. So there are 5 terms given here. So I have, okay, and then I have that x value is tabulated at that point. Okay, 0, 1, 3, 4, and 6. Okay, normally this is given to us. Okay, and we construct the polynomial. Just to demonstrate the error in this whole method, we are actually using this functional form of f here, okay, to get this numbers. Okay, this is not something which we will encounter in real life. Okay, that is, if you know the functional form, then we don't need all these tables. But this is just to demonstrate that we construct this table, okay, from a known function and then look at what is the error in our derivatives. So I use this function here f of x equal to x squared minus 2x plus 2 to actually tabulate this function values here. So function values at x equal to 0 is 2, x equal to 1 is 1, 3 is 5, 4 is 10, and 6 is 26. So we have just tabulated this at this 5 different points. Okay, that is the first order. And then the next one would be to compute the f xi plus 1. Okay, that is terms of this type. Okay, the f x0 x1, and the next would be f x1 x2 etc. Okay. So that will be, so that's equal to f of x2 minus f of x1 divided by x2 minus x1, and we go on like that for all the pairs. So we take each of these pairs and then we compute the next one, and then we take each of these pairs and then compute the next one, etc. Okay, so we can see that this is the function values, and this is the difference between these 2 points divided by the difference between these 2 points, and this is the difference between these 2 points divided by the difference between these 2 values, and this is the difference between these 2 values divided by the difference between these 2, and this one is difference between 26 and 10 divided by the difference between 6 and 4. Okay. And then the next level, that is the third order term in the polynomial, then is given by the difference between these two, that is 2n minus 1 here, and the x value difference between 3 and 0. Right. So, and the next one is the difference between 5 and 2 divided by the difference between 4 and 1. Okay. So, that is x0, this is the third order term, and then we can do the next one, the fourth order term in the polynomial, and then the fourth order term in the polynomial, and then the fifth, etc. Okay. The fourth order, I mean the function with 4 variables in there. Okay. The coefficient which takes 4 points into consideration, and then the fifth point, etc. So these things are 0 because our polynomial, this whole when a function actually comes from a polynomial of order 2. So we obviously getting the higher order terms as 0. Now let us say we want to evaluate, so we have this table, okay, we have a difference table constructed. Okay. So it could be any set of data points given to you from some experiments or some simulations or some other function. I given you this function values at this tabulated values of x, and then we construct this difference table, and from this difference table we can write down this polynomial. So since we have all these quantities, we can write down this polynomial, and then from that polynomial we can write down the derivative of the polynomial. So let's evaluate the derivative at any point, let's say between 3 and 4. Okay. So now if you want to evaluate the derivative between 3 and 4, right, I could take a second order polynomial, a third order polynomial, or a first order polynomial. Okay. So we will see that example. Okay. So we will take a polynomial which goes through, for example, 0, 1, 3 and 4. Okay. Or we could take a polynomial which goes through 1, 3, 4 and 6. Right. So we can construct 2 such polynomials, that is 2 polynomials of the same order. One goes through 0, 1, 3 and 4. Okay. So that gives us a third order polynomial, and there is another polynomial which goes through 1, 3, 4 and 6. So there are 2 such polynomials which we can construct to evaluate a derivative between 3 and 4. Okay. Since both these polynomials pass through 3 and 4, we should be able to evaluate a derivative between 3 and 4 using that. So that is what we would see. Okay. So x equal to 3.2, for example, we will take, okay, and then we will try to calculate this polynomial. So the derivative of such a polynomial, of a third order polynomial, will be is given here. So let us first construct the third order polynomial which goes through from this table. Okay. So if I want to construct a polynomial which goes through 1, 3, 4 and 6, so we have 4 points. Okay. So the polynomial will be given by 1 plus 2 into x minus 1 plus 1 into x minus 3 plus 0 into x minus 3 into x minus 4, etc. So let me write that down here. So we are looking at a polynomial which goes through I think function x1, x values as 1, 3, 4 and 6, 1, 3, 4 and 6. Okay. So that's a function where we are going to through. So the xi's are given by that, 1, 3, 4 and 6. So polynomial of third order polynomial Pn of x, we will write as f of x0, x0 is 1 now. So f of x0 in this particular case, f of x0 is 1, right, because we are going to start from here. So x0 is 1, so it's 1 is like 1 plus 2 into x minus x0 is 1. So 2 is the next term. Okay, it's f of x0 x1 is 2, f of x0 x1 is 2, so that is the next term. Okay. And then so 2 into x minus x1, and then we have the next term, that is f of x0 x1 x2, that is f of 1, 3, 4. Okay, that is 1 again. So that is the next term, that is would be 1 into x minus 1, x minus x0 into x minus x1, that is 3. Okay, so that is 1, and the next term in this thing would be plus the next term. The next term coefficient is 0. Okay, so that doesn't bother us, but anyways we will write that 0 into x minus 1 into x minus 3 into x minus 4. Okay. So that is the third order polynomial which we will have. So the derivative of this third order polynomial at any point would be is 2 from this plus, so now there are two terms here, so 1 into, so we have a term x minus 1 then plus x minus 3, okay, and the last term doesn't exist. Okay, so that gives us the polynomial, so that gives us as 2x minus 2 as the answer of the derivative and evaluate at any point. So you can see that from the function here, which is x squared minus 2x plus 2, the derivative is 2x minus 2. So it looks like this third order polynomial which we constructed and we took the derivative, the derivative is exact. Okay. So that is need not be always true, but in this particular case it is exact. Okay. So what we just did was this, that is 1, 2, 3 and 4, that the equations with the x values which we took was x1, x2, x3 and x4, okay, and we constructed that polynomial and we found the derivative to be 2x minus 2. We can do exactly the same for 0, 1, 2 and 3, and we would find that we get exactly the same derivative in this case as 2x minus 2. Okay, so what we have to do is take 0, 1, 2, 0, 1, 2 and 3, that is the x value 0, 1, 3 and 4, okay, and we can read off the polynomial from this using this set of values now, that is 2 minus 1, 1 and 0, okay, and we can write the polynomial and then its derivative is again given by this one, that is 2x minus 2, okay, which is the same as above, right. So we get two third order polynomials which goes through this point x equal to 3.2 at which we want to evaluate the function, okay, and we find that even before evaluating it that the derivative is exact because we knew we were looking at a function of this form, the values are tabulated from the real function which is x squared minus 2x plus 2. Okay. So then now we can just try to look at a second order polynomial, that is the derivative being first order, okay, so we can look at that, okay, and then you can compute what the error in that would be. Okay. So here in this case we just look at a first order polynomial, and if you look at a first order polynomial which goes through 2 and 3 for example, okay, let us see, we want to evaluate something here, okay, some derivative between 3 and 4. So we just construct a linear a line which connects 3 and 4, okay, that is 3, 5, 4, 10 as a function value, okay, and then we will evaluate the derivative between that. Okay, so the polynomial is given by 5, right, plus 5 into x minus 3. So the derivative would be just the linear function would be 5 plus 5 into x minus 3, okay, and then you can just look at the derivative of that, okay, that will be just 5. Okay, so that is what we will find here. Okay. So the derivative is simply 5. Okay, so polynomial, remember that a linear polynomial which goes through these 2 points, okay, would be just 5 plus 5 into x minus 3. Okay, so the derivative of that would be just 5. Right, so we have a constant there, that is derivative is 5, but we know that the derivative is 2x minus 2 with x equal to 3.2, which is 4.4. Okay. So we are off by 0.6 by going to a linear interpolation between 2 points in which brackets the value at which we want to evaluate the derivative. We get an error 4.6. Okay, so we just wrote down a polynomial of order 1, okay, and we said that was 5 plus 5 into x minus 3. Okay, so we had used here xi as just 3 and 4. Okay, so we got it's 5 plus 5 into x minus 3. So the derivative was equal to 5. But at 3.2 the derivative should be 4.4, okay, so the error is 0.6. And then now we use our idea that the error should be like the next term in the polynomial. So what is the next term in the polynomial? So what is the error in this polynomial? So error in this polynomial would be some coefficient here which I do not know, okay, some coefficient, okay, or that if I just write a second order polynomial here, okay. So then this term should be just 1 into x minus 3 into x minus 4, okay, that is the term which I have written here, because after 5 the next coefficient is 1. So the next polynomial term is actually x minus 3 into x minus 4. So this is my error term. Okay, so if I write a first order polynomial, this is my first order polynomial. The error in the polynomial is like that. Okay, that's the next term in the polynomial. Okay. So that's we have error in the polynomial. So then if I say what is the error in my derivative, and that will be of this order, and that would be maybe 1 into x minus 3. So that is 3.2 minus 3 plus 3.2 minus 4. Okay, so that would be the error in the polynomial, right? So substituting x as 3.2, evaluating at x equal to 3.2, okay, or in general it should be of the type that it is equal to okay, so if I substitute x equal to 3.2, I will find that this is 0.6. Okay, so that's what I am summarizing here. Okay, so if I use a first order polynomial, and then I use the fact that the error in this polynomial is like the next term in the polynomial. Okay, so then I write the next term in the polynomial, and then I say then I can compute the error from this. The derivative of this is the error in my derivative, and then if I evaluate it at x equal to 3.2, I will get it as minus 0.6. So our value which we found was 5, and the error was 0.6. So and we know the actual value is 0.4. So we see that this gives us a good idea. Here in this particular example, it is exact, but this may not be exact always, but it will give us a good estimate of what the error is by just finding the derivative of the next term in the polynomial. So that's and we will look at so this is one method of finding the derivative of a set of data points, derivative in between a given set of data points by actually interpolating these points by a polynomial and then taking the derivative of that polynomial. And we know that if you have the difference table, then it is easy to construct this derivative because it is another polynomial which can be written in terms of the difference table values. So that is one method. We look at other methods and of finding the derivative and discrete derivatives in the coming classes.